Now I'm very pleased to serve as the chairperson of this section, Further Developments, and it is my great pleasure and honor to introduce our first presenter, Professor Christian Huck from Austria. Professor Huck is currently Vice Head of the Institute of Analytical Chemistry and Radiochemistry and Head of the Spectroscopy Unit in University of Innsbruck. He is a real pioneer in the field of vibrational spectroscopy with more than 300 peer-reviewed papers published with age index of 52 and more than 10,000 citations. It's amazing. Professor Huck received the Thomas Hirschfeld Award in 2018, beside further numerous prestigious awards. He has a long relation with Professor Chenkova, as we heard this morning in the video speech as well, and Aquaphotomics, and he visited Japan several times for research purposes, and today he is going to talk about modern tools of near spectroscopy in water-related analysis, miniaturized spectrometers, quantum chemistry, and neural networks. Dear Christian, please deliver your speech.
Okay, just have to see. I need to share my screen.
And in the meantime, just a few more words. I would like to highly encourage the audience to type if they have any question during the presentation, and I will read them at the end of the presentation.
So
thank you,
Christian. You should see my screen now?
Yes, we can see it.
Okay. Yeah, so thank you very much, Zoltan, for your very kind introduction. It's a huge pleasure to attend this meeting and also a honor. And at first, I want to congratulate the organizers again. It's not easy in this pandemic time to keep all the members of the Aquaphotomics Society together, and I think you're really doing a great job. Furthermore, I also want to take this as an opportunity to thank especially Rumiana Zenkova for our very long-lasting friendship and collaboration. And I'm sure your time will continue very busy as it used to be. And I'm looking really very much forward to continue our very strong collaboration. Now today, I will take approximately the next 25 minutes to give you an idea about the modern tools of NIR spectroscopy in water-related analysis. I will focus on miniaturized spectrometers, including quantum chemistry and also neural networks. So, the topics in scope of this presentation are, at first, I want to discuss the unique potential of NIR spectroscopy in modern analytical chemistry. And I want to give you an idea about the revolution in miniaturization, especially of NIR instrumentation. Today, we have the opportunity to use advanced techniques, including quantum chemistry, two-dimensional correlation spectroscopy, nonlinear regression, and also neural networks. I want to give you a short idea about basic research, instrument evaluation, development of new methodologies, and analytical applications we are currently carrying out in this field. As my talk is intended to give you almost an overview, I want to point your attention to two further very highly interesting talks which will be provided by my co-workers and co-authors of this talk. It's at first Dr. Christoph Betsch. He will talk on Monday at 5:50 Japan time about the nonlinear regression and artificial neural networks in NR spectroscopy, giving insights into fundamental phenomena and impact on practical application in water-related scenarios. And also Dr. Justina Grabska, she will speak on Sunday, tomorrow at 5:15 about water structure and water mirror effect in NR region, a perspective from quantum chemical simulations. So I highly recommend you these presentations because they will give you much more detailed insights into the work carrying out in our laboratory in this field. Now, why do we still need analytical innovation? I think we have a very huge demand all over the world to make further developments because at first, all our analytical methods, they are not fast enough. We have to see how we can increase the speed of the analysis. We want to analyze in high sample throughput mode. Also, sensitivity is always a problem. Especially if you compare vibrational spectroscopic methods with, for example, mass spectrometry. Here we are always lacking sensitivity, so we have to see how we can improve the detection limit. Selectivity is also a problem because sometimes vibrational spectroscopy is not so selective. So we have to find a way how we can analyze the needle in the haystack. And by optimizing these three parameters, we could really enhance the efficiency. And the final aim should be to see something that we could not see before. So at our institute, we are not only focusing on vibrational spectroscopy, nevertheless, this is our main topic. We are also covering a broad field of analytical chemistry. At first, sample pretreatment techniques, meaning enrichment, solid phase extraction, helping to pre-concentrate, low-concentrated analytes in complex matrices. And this, of course, can then be combined with ongoing vibrational spectroscopic analysis. Separation methods like liquid chromatography, miniaturized, even hyphenated to mass spectrometry or screening techniques based on different mass spectrometric techniques, they can be highly useful to establish highly powerful calibration validation models using near-infrared, mid-infrared imaging mapping techniques and also Raman spectroscopic techniques. Now, if we go back to the very fundamental basics and we have a look at the electromagnetic radiation, we see here the IR region between the visible part of the UV spectrum and the microwave region. And today we know that the IR region can be divided into three parts. At first, the NIR region, the near infrared region, near to the visible part, in the range between 12,500 to 4,000 centimeters reciprocal. Then the mid-infrared region following 4,000 to 400 and the far infrared region. So my talk today will mainly focus on the near-infrared region part. What is the origin, in principle, of a mid and a near-infrared spectroscopy? And this goes back to the model of the harmonic oscillator. Imagine we have a molecule consisting of two atoms with their atomic mass m and capital M. And now this model starts to vibrate, and we have here this frequency of the oscillator, which is defined 1 divided by 2b multiplied with the square of k divided by mu, the reduced mass. And the harmonic oscillator tells us that if we now scratch or squeeze this molecule that we can adjust the first excited stage only. So this only describes the effect appearing in the mid-infrared region. Now today, we know in near-infrared, we observe a high number of overtones and combination vibrations. This means that not only the first excited state, but also the second, the third, or the fourth excited state can be adjusted. And to describe this phenomena with physical chemistry methodologies here, the anharmonicity constant has to be introduced into this equation, and the whole potential curve gives a completely different shape. From this, it becomes clear that near-infrared spectroscopy must be less intense than mid-infrared spectroscopy, but on the other side, it contains a lot of more information than mid-infrared spectroscopy. So what information is available from near-infrared spectra of materials in general? If you look here at the NIR spectrum of aspirin and cellulose, you see they give a completely different fingerprint spectrum. So it's not difficult just by eye to differentiate between those two. Now, this can be used to analyze chemical and also physical properties. And this can be used as a fingerprint for the identification and characterization. And for this purpose, near-infrared spectroscopy is especially very powerful. Now, Yuki Osaki already showed us this spectrum here. And this is the absorption index of water bands. And it has to be noticed that it's 100 times lower in NIR region than in IR region. The presence of water in the sample often leads to complete absorption of IR radiation, and only with attenuated total reflection in the mid-IR region approach, a successful measurement may be performed. In contrast, NIR spectroscopy may be used directly. And this makes NIR spectroscopy far more suitable for examination of such samples. What can near-infrared spectroscopy be applied to, including aquaphotomics? One hot topic we are focusing in detail is here in our laboratory in Innsbruck, the applicability of NIR spectroscopy with exemplary scenarios in which water is present, covering medicinal plant analysis and production. And this starts already with the seeding and growing on the field, and then doing all the analytical quality control, doing the extraction of the raw material, the whole industrial process, the final product, and finally we are analyzing the potent ingredients also in human body fluids. So we want to ensure a whole quality control from the field to the patients in patient blood and urine. Now, I told you I will also speak a little bit about miniaturization, because now all over the world, there's a huge trend towards this miniaturization. I know this year several new companies will appear on the market with very powerful new near-infrared spectrometers covering different wave number ranges, different resolution, and so on. And if you look at this slide, what happened between 1940 and 2021, it's really amazing. In the beginning, we had these huge instruments, and now since 2008, they are becoming smaller, 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 and also cheaper. And it was already some years ago. It was a Fraunhofer Institute in Germany. They published a paper where they included a smart NIR spectrometer into a smartphone. And now a company in the United States, Viavi, they are working very hard with a company in Spain to bring out a new smartphone using infrared spectroscopy portable devices. So question is, where will it go? Will it work for our purposes to measure medicinal plants on the field or even the tablet? Can it be used for food and quality control and other applications? So this is really a very critical question. It's not enough just to spend the money and to buy it. So we have to look what's happening behind the curtain. And if you look now to miniaturized instruments, it must be clear that the difference in price must have a deep impact on the different performance. So what you see in this slide is one benchtop instrument. In this case, it's a Büchi Nerflex N500 instrument. And these two portable devices, one is the microphaser and the other one is the micro NR 2200. They are operating in completely different wave number ranges with different resolution. So it's obvious that there is a huge difference in the performance. Today, there are several instruments on the markets and they are following completely different design philosophies. This means their operational characteristics and as a result, the performance in different applications vary quite significantly. In our group, we evaluate these characteristics and we develop strategies oriented at optimizing the applications of these instruments down to best performance and applicability. For optimizing especially miniaturized systems, we have developed during the last years this workflow. You see here at the bottom, we are recording spectra with a benchtop device and on the right side also the miniaturized device. Then we have here on the left side quantum chemical calculation, which can be taken into consideration for simulating spectra and being highly useful and helpful for very distinct band assignment. On the right side, we also use, of course, different reference methods, but also multivariate data analysis, including advanced techniques like two-dimensional correlation spectroscopy or multivariate limit of detection. And this finally brings us to a critical evaluation and helps to optimize the whole analytical procedure, especially if you want to use miniaturized instruments. This is, for example, now used for the analysis on the field. We started in the beginning with our Vena officinalis, going on the field, doing direct measurements on the plant to estimate the optimum harvest time. And now this technology has been expanded to all these plants. You see here, Primula veris, Rumex acetosa, Timian, Gentiana, Luteas, Cimicifuga. This method is now used in Europe, in the island of Mallorca in Spain. It's used in Montenegro, it's used in Russia. So this seems to be very powerful with a lot of future potential. Now coming to quantum chemical calculation, and this is a methodology which was transferred from Professor Yukihiro Saki's lab, where I met in 2014-15 two of his postdoc students at this time. It's Dr. Christoph Betsch and Dr. Justina Grabska. And since now almost 2 years, they have joined my lab in Innsbruck, so we can continue with this very powerful technique. What they do is they simulate the NIR spectrum, and you can see here they are able to simulate the different parts, for example, first overtone, binary combinations, and so on. And the simulated spectra agrees extremely well to the calculated one. What in our lab is going on with this quantum chemical simulation methods is that, for example, we calculate the spectra for different constituents in medicine plants, which is shown as an example here for thymol, for rosmarinic acid, and several others. So especially for small molecules, it works extremely well. This technique has been further enhanced by the two colleagues, and they established a method depicting the results in this heat map. This heat map shows you on the left side the different contributions to the NIR spectrum, and the color gives you an idea about the importance and the intensity of the individual distribution. So from this map, you can deduce which contribution to the NIR spectrum is directly important and has a direct influence or not. Now, what we can see here is that we can simulate and explain the very subtle effects that are related to how the NIR spectral signal of a molecule surrounded by water is effectively enhanced. This is a concept of water mirror and is known in aquaphotomics. It has been reproduced from the first principles and become better understood through our research we are currently continue to conduct in Innsbruck. More details about this study, which is really very highly interesting, will be presented by Jelena Muncan in her talk on Sunday at 5:15 at Japan time. Finally, I would like to briefly mention that recently we investigated the water NIR spectrum itself. For the first time, our results unveiled that the band structure of water is more complex than previously assumed. Each contributing species features more complex band shape, for example, with double peaks as presented on the right. And again, Dr. Jelena Muncan will present the details of our findings in her talk on Sunday, 5:15. Two-dimensional correlation spectroscopy is a very powerful method as the eye of the spectrometer. What I show you here now in the next slide is the analysis of rosmarinic acid as a potent ingredient in powdered rosemary leaves. We investigated 60 samples. And what you see here on the left side is the 2D spectrum of Büchi benchtop Neurflex N500 instrument. And on the right side, the 2D spectrum of the miniaturized microphaser instrument. So you can see here on the right side that here an outer peak is appearing, which is almost missing in the 2D spectrum of the benchtop device. What does it mean? It means that this special peak here with microphaser is extremely important for establishing the calibration and validation model. So without performing two-dimensional correlation spectroscopy, we would never have been able to find out that especially this region must be used for linear regression vector analysis. And if you do this type of optimization, 2D codes analysis, including quantum chemistry, you will be able to establish models which are very powerful, even using these handheld devices. You see here that with this methodology, we can analyze rosmarinic acid in these dried plant samples with SCP in percentage of 0.07 with the benchtop instrument, and with microphaser and micro NIR, we are almost in the same range. So if you design and tailor your method really very efficiently, you can very nicely use these miniaturized instruments. Another example is the analysis of potent ingredients in Verbena officinalis for judging when will be the optimum harvest time. So in this case, we conducted the direct measurements on the plant, analyzing for verbenalin and verbasco seed in this Verbena officinalis plant, which is used against mild sinusitis, also against the cold. And we found out that it's very good to use this miniaturized technique because depending on sunlight and humidity in the plant, the concentration of this potent ingredient might change fundamentally. So you need a technique where you can easily measure and then decide you want to harvest now or you want to wait. And there was also a very nice paper from Rumiana and Jelena, also focusing on the water content for the same purpose. So this could be one approach which could be really combined in our collaboration for the future. Such methods can also be used for at-line monitoring, for example, of extraction process. Here we investigated also rosmarine folium, and we checked for the health potential, like antioxidative potential. And we found out that using these miniaturized techniques, almost you have 100% agreement with all the available reference methods being based on liquid chromatography or even wet chemical analysis. Now, this is one of our latest work we have just published a few weeks ago, and this study demonstrated that the performance of miniaturized instruments can be improved to become equal with the benchtop spectrometers if more advanced methods for calibrations are used. And the application was the moisture content analysis in plant material using these miniaturized spectrometers. This is still a very important scientific question in the field, which has a direct impact on the quality. Now, very briefly, coming to extended chemometrical methods like nonlinear regression and neuronal networks. So in this case, here we have taken into consideration two benchtop instruments, Nirflex N500 from Büchi and Bruker NPA. And the table shows that the PLS regression can only perform well for benchtop spectrometers and the idealized sample treated with drying agent. If one wants to use miniaturized instruments with PLS, the prediction performance is much lower. However, with advanced neuronal and advanced chemometric approaches like GPR and ANN, that reduction in performance is noticeably lower. And about this, more details will be presented by Dr. Christoph Betsch in his talk tomorrow at 5:15. Now I'm coming towards the end of my presentation, and one thing which will become extremely important in the future, especially in precision agriculture, is the use of drone systems. And this will also include the application of miniaturized spectrometers, and with this, the same problems and solutions will be applied. But it offers, of course, new insights into quality control already during breeding procedures, and we are currently conducting research in this field within a Horizon 2020 project with several partners all over the world. So I'm coming to the end with my overview. I want to point your attention to the book recently published just before Christmas about near-infrared spectroscopy, series spectral analysis, instrumentation and applications with editor Sosaki, myself, Satoru Tsuchikawa and Soren Engelsen. And finally, please don't forget, NIR 2023 will be held in Innsbruck with myself as a chair. And I think By then, we all will have vaccination, so you can all come to Innsbruck to share our new findings also about aquaphotomics, and I'm looking very much forward to welcome and see you all here. And with this, I want to thank again the organizers for giving me opportunity to give this overview. Thank you very much for your kind attention. And with this, I give the word back to the chair, Professor Zoltan Kovacs. Thank you very much.
Dear Christian, thank you very much. Especially thank you for keeping the time precisely. You always steal my attention showing these wonderful pictures about Innsbruck at the end of your presentation. So thank you very much for this very nice presentation, the very nice technical overview of infrared spectroscopy. Is someone talking? All right. You can hear me, right? Okay, I can hear someone else is speaking too. Is there any question from the audience?
Yeah. Hi, Professor Huck. I have one question. Thank you very much for your wonderful presentation. I just see one page about you see the AIR spectra is better than IR spectra. And in that finger, you just use the far UV, VIS, AIR, and IR spectra together for the water. So I just wonder, this finger is made by one instrument, or you just buy different instrument and they made the signal together?
Okay, I think I did not really understand your question, but I think it's related, including FUV, far UV spectroscopy. First, I have to say that I'm not the specialist for far UV. That for this topic, I would directly relate it to Professor Saki Sensei. What the meaning was that in mid-infrared, the intensity of water is so high that normally you have to apply ATR-IR spectroscopy to get a very, very nice spectra. And in near-infrared, the intensity is lower, so you can directly investigate all the different water bands.
Okay, thank you.
You're welcome.
Thank you very much for the question. And in the meantime, we got a question in the text box. I think it's available for you too, Christian, but I can read it for you. Linked to the handheld devices, do you see an opportunity to make a holistic picture of a whole ecosystem in the field? Let's say, for example, a lake or a glacier.
Yeah, we did not try this before. Concerning the question with the glacier, that's maybe something interesting, and I would highly recommend you tomorrow the talk at 4:45. There will be a talk from Christina Donauer from our university in Innsbruck, but from a different Institute of Physical Chemistry. And she will speak about extending the spectrum and AR spectroscopy of crystalline water ices. So if you are talking about glaciers, this might be a good hint that different forms of ices, also including different other parameters, can be discriminated. But looking really at lakes, we did it not, but I know, I don't know if you know Phil Williams, one of the fathers of NIR spectroscopy. And very early in his career, he investigated different parts of the ocean all over the world. And he could show that with near-infrared spectroscopy, you're able to discriminate the origin of the water samples, if they are from Atlantic Ocean or from Pacific and so on. So based on this, I would say in a very careful answer to your question, I see potential that this might work. That's all I can say so far.
Okay, thank you for the answer. Yeah.
Thank you very much. I'm afraid we have to stop now because time flies. Thank you very much once again for your wonderful presentation. And I think if possible, we could continue in the break. And now I would like to invite our next presenter. It's my very big honor to introduce Mr. Shogo Shigeoka. I was very fortunate to work in the field of aquaphotomics in Japan for 3 years when I first met Mr. Shigeoka. And there I met only very kind people. But I have to say that Mr. Shigeoka is one of the kindest I ever met, even among Japanese. But beside that, Mr. Shigeoka, as president of SPA Yunosato Shigeoka CEO Ltd, has been always very open and extremely supportive to aquaphotomics research, collaborating with Kobe University and Professor Chenkova in doing deep research of the 3 types of waters of Yunosato, but also related to all phenomena of water in general. What shows Mr. Shigeoka's extremely high interest, support, and commitments towards water science and aquaphotomics research is that he established Yunosato Aquaphotomics Lab as a really unique facility to provide an ideal space where the 10 years long collaborative research can be continued and the knowledge acquired through the joint research can be utilized. I would like to take the opportunity to congratulate for this huge achievement and for the 10th anniversary of the collaborative research and express my greatest gratitude for the immense support to the aquaphotomics research. And with this, I would like to invite you, Mr. Shigeoka, to deliver your presentation titled Aquaphotomics Laboratory in Yunosato. The floor is yours, please.
はい。ドルタさん、丁寧なご紹介ありがとうございます。
Thank you very much for your kind introduction. I am very pleased to be able to speak in this academic opportunity, and I would like to extend my thanks to all the people, including Professor Chenkova and staff members. I'm different from all the professors or doctors presenting here today, but I am a person representing a company. I'm here in that space. Why I am interested in aquaphotomics, even if I'm not a scientist, why I have built the laboratory. I would like to explain that history. I am the president of Shigeoka Limited. Yunosato is located in Hashimoto city of Wakayama. It is called Konono. In front of that, we have the Koya-san World Heritage Site. About 1300 years ago, there was the temple called Konono Temple. So it has a long history, very important history. We have water, what we call gold water, silver water, and bronze water. Each has unique characteristics. Our company was founded in 1987, about 30 years ago. The first water we got is gold water coming from 50 meters deep in the ground. There was a limited earthquake in Hashimoto city, and this water coming up immediately after the earthquake, and there is a lot of volume. And next one is the silver water. This is from the deep, more than 1,000 meters. This is a hot water, hot spring water. There is a big rock, and originally those water was trapped into the rock, and after that it was found. The last one is bronze water. This is also unique water. Particularly for the silver water, hot spring water, the people experience improvement of health status. Many people said that this water is good for their health. This is our facilities. Here we have the hot spring facility and also the hotel. And we have restaurant and super. And around that, we have a huge organic farming area. And we produce vegetables, and those are turned into products like dressings. And at the same facilities, we built the Aquaphotomics laboratory last year. These are the products we are producing. Some of the examples. The main product is the combination of gold water and silver water. This is a mineral water called Tsuki no Shizuku. That is the brand name of the water. And by using that water, we produce cosmetics. And as I said earlier, using the vegetable from our farming, we have dressings, and also we have developed yogurt and produce it. Tsuki no Shizuku is a branded mineral water that was released in 1995. When it was released, many people said that it was good for their health. Many voiced the effect of our water, Tsuki no Shizuku. There are some researchers who are interested in our water, and they visited Yunosato. And some issued the guidebook, and one of them said that this is the best water I ever encountered. That was a comment we received. And also the place called Konono, that is a place related to the Buddhist monk Kukai, who opened Koyasan, and he offered prophecy that later this place will offer water which help many people. So just like the prophecy, we may have this water. So there were people who authored the books about the Kukai and water. And there are magazines and journals who talk about the water, our water, how wonderful it is. So when we talk about hot spring, we look at the solute and the mineral balance and the conductivity, and there are many elements that can be measured. And many people looked at our water for measurement. But we got the actual story from the customers, and those measurement results are not directly related to our stories or our customer's story. And in 2005, Professor Tsenkova visited us because she heard some rumor about water. So that was my first encounter with Professor Tsenkova. 2005 is the year when Professor Tsenkova announced the new concept of aquaphotomics. When I met her for the first time, I listened to a lot of concepts, light and water correlations and interactions. If we can elucidate it, that can elucidate everything in the universe. I think that is something she told to me at that time. It was so impressive. There are something we cannot explain about our water, but probably this person, Professor Tsenkova, may give us a hint so that we can elucidate the secret of our water. So that was a very exciting encounter. Then after that, she applied aquaphotomics science to our water. And in 2011, there was a conclusion saying that that is a very unique water. And in the following year, we started the collaborative research between Kobe University and Yunosato. Professor Tsenkova mentioned the following point. There are a lot of inspiring comments. Water connects everything everywhere. Even if we look at each component of water, it doesn't tell you a story. Water connects everything. the temperature, humidity, light, there are perturbations, and water is affected by those perturbations. Water component doesn't directly define the functionality. Water structure defines the functionality. That is what she said. Please look at this picture. This is the tap water of Hashimoto City, and this is the photo of a mineral deposit after evaporation. I took this photo. In the case of tap water, in most of the cases, the mineral deposit comes to the edge of the water. And this is silver water, our hot spring water. Under the same condition of experiment, the mineral deposit shape, as you look, are so different. It is dispersed, not collected. And if you do the same with Tsuki-no-shizuku, more dynamic picture, it's like a living system, beautiful crystalline like shapes. So it's not component. The relationship with water may define functionality. I think that can be sensed using these photos. Everything is connected and the functionality is in that relationship. The water has an immense power to adapt to environment by constantly changing its structure. Water is stimulated by surrounding environment, and then water adapts itself to environment. This is something I learned from Professor Chenkova. So when we look at water, we need to look at it in combination with environment. That's what I learned. In 2011, we started our initiative. Every day, water spectral is checked. Every day for 1 month, we took the data and then that was sent to Professor Chenkova. Every day we take data, so that cannot be done by one person. So I assigned 2 people. I was surprised because all those data were taken by 2 people, but the university analyzed that which one was taken by this person, which one was taken by another person. So that was clearly separated. So that means that the samplers impact or samplers effect is shown in the water. So by looking at the data, they recognize which person take the sample. So where and who and what is the temperature and the humidity and the moon stage, all the information was collected. So data was sent together with all those associated information. So this is the spectrometers we have in Yunosato. As Dr. Huck explained, there are some new devices, and we are using some of the new devices. Micro NIR is also one of them. So we've got a lot of data, and water spectral and environment, how they are connected. We had analysis. Here is the data. Dr. Zoltan, Dr. Chenkova, all of them give analysis to these data. The temperature versus water. When you look at the annual average, gold water correlation 0.9998. So water and temperature has a good correlation. As mentioned earlier, water is sensitive to temperature, but depending on the type of the water, sensitivity is different. The gold water has a most high correlation with temperature. And also humidity versus water, there is a high correlation again. The water molecule in the air and water molecule in glass, there are always interactions. The last one, this is the surprising one. The Professor Chenkova said that there is a time-related changes in water. So we wanted to see the data to see there's any prediction we can do. So we use moon age or moon stage information for the analysis. In gold water, silver water, there is no correlation at all. But if you look at the Tsukinoshizuku branded water, 0.997, the beautiful correlation is shown. So this is related to moon stage. And starting from the new moon and then full moon, and this is a 1 month movement.
So the interesting thing about this is that we do this every month. So from the new moon to the old moon for 1 month, we take the data. So if we do that, it's not on a monthly pace, but if we take more time, then we can actually not see it. So it's really important that this is taken on a monthly rate. And we understood, we were told that they understood why it's called Tsukino Shizuku, which is a drop of the moon, how the one drop is affected by the moon. So it is amazing how the water was actually connected to time and all the other factors surrounding the water. So water does change depending on the environment, and by changing, it stays stable. So it's important that we take a look at it with a long span, not just the momentum things. So when you think about it, for example, Tsukino Shizuku, the water, it's very stable, and this is of course the result of something that happens over time. So this is the gold, silver, and bronze, the three different kinds of water. So even though it's from the same place, you can see that how the three different waters are very different. So from here, we would like to talk about further application of aquaphotomics to produce things. This is Professor Zoltan Kovacs and Professor Chenkova. They collaborated a paper about the water. As I said, the water, where, who, temperature, humidity, all the things, the changes, the area of changes can all be seen in the characteristics of each water. So if we add some sodium to it, the water will change. So using these kind of techniques, we have been taking the data of different situations for a period of time. So because we have been doing that, we have noticed that the gold water is very stable. And there is a river in front of our facility, and it's called River Tree. And it's not like it has always been stable. When we did our research, because we provide the water to people, we filter the water, and we actually did research on the contamination on the filters, and we found out a lot of important information in the filter. So yes, we provide mineral water to keep the contents, to keep the quality of the water. It is very costly to do that. But by doing this every day, we're actually monitoring the water every day. So when it becomes a product, all the data has been very helpful to have a better understanding of how the apple water can be applied. Here is a publication of Alexander Slavchek from Bulgarian. So this is the water spectral pattern, probiotics growth when used for rapid bacteria selection. So by observing the water, you can actually select the bacteria in the water, so the probiotics. So if you can see here, the lactose in the water, you can see this red part, the probiotics will affect the body. So we have been researching and developing a yogurt using soy milk. So here is the probiotics from Bulgaria, the S10, and Lactobacillus rhamnos is another very strong biotic. So in the soy milk, we put in 10% of our water. So we use different kinds of water that we have. So, and we have 5 different mixes. So with like 1 probiotics or bacteria, or like more probiotics, bacteria, or how much the water content was, all differs. So by looking at this chart, you can see that we have been combining the water and soy milk in 10 different groups. So what is very interesting is that when we only have 1 probiotics, we can see that, you can see that it's quite strong. But if we use 2 probiotics, it's going to reverse. So just using 1 probiotics, that is something very powerful. But in reality, it is quite normal that there is more than 2 things present in a substance. So we thought it was important that to know about what happens when there's more than 1 bacteria involved in the product. So, like you can see here, here is number 7 and number 2. We have the 2 different kinds of yogurts that we sell now. So it's Sasho. Alexander's nickname is Sasho, and that's why we decided to call it Sasho yogurt. It has been very popular ever since it has been on sale. And the stomach condition is quite good, and they feel like the absorbing of the stomach has improved. People with allergies, when they keep on eating yogurt, the allergies also became much better, was improved. So it has been helping people we've been hearing from people that has been helping improve their health conditions. So we're very happy to hear about that. And here we have a series of cosmetics. So there's a serum and a lotion and cream. Of course, we put our water in the cosmetics. The energy balance, the best energy balance is picked to produce our cosmetics. So, ever since 2011, we have been sharing and doing research together, and the data has become quite big. So 50,000, more than 8,000 spectrums. And of course, the hot springs also provide a lot of data. So we ask people to check their condition before taking a bath and after taking a bath, drinking water also. So all these data has actually been piling up, and we have a big number of data. And so my idea was we need to use this data. We can't let this go to waste. And that was why we decided to make this Aquaphotomics laboratory, to make the best use of all the data we have. So if you take a look here, this was the this is the inside of the lab, as you can see. And there is an area where the products are. So here are the people in our lab. There are 6 people working in the lab, and with Professor Tsenkova, daily research has been conducted. The middle part is a very unique, creative space in the building. Sono Masayuki from New York designed this. This place is for meetings. I think in the lab, people are watching this conference today in our lab. These are the equipments that we have. This is where we take the data. So what does our future look like? What we want to do in the near future? So FEC is a name of a company. This is a vacuum drying unit made by FEC. So inside it's minus 98 kilopascal, and the water temperature is about 35 degrees. That's when the water actually starts to evaporate. So in this machine, we put like vegetables and food. So by putting the food in this drying unit, the water will evaporate. So what remains is the dried food inside the measure. It is a very good product, what we have. The very well vacuumed, dried product, but we are actually interested in the water, not the product that remains. So we are collecting the data and analyzing it. Without the water, all the products are something very different. Here, we have the three waters: gold water, silver water, and bronze water. This is an equipment that blends the three different kinds of water. By the way we mix these waters, by the way we blend these water, there will be a difference. And of course, the ratio too is going to affect the outcome. So 2, 1, 1, 3, 1, 1, 4, 1, 1. If the ratio changes, there's a big difference in the outcome. So by combining different kinds of waters, we are able to make different kinds of water. And so, and adding to that, we use the water we took from the vacuum drying unit. We add that to the waters blended in this machine, and the combination is unlimited. And so to apply the characteristics of this water, as we said, we are applying this to cosmetics, of course, to farming, because we took the water from the fruit, so we get it back to the fruit. So yes, in our organic farm, we are researching how the products will differ depending on what kind of water they get. Of course, fruit products and the water to products too. We are trying to apply all the technology to our products. So I feel very honored to take part of this aquaphotomics science field, and it's been an honor to share this moment with scientists all over the world. So, like the water, I hope the world will be a nice blended water, and a very luminous future is what I am hoping for. Thank you very much.
Thank you very much for this very nice and colorful presentation. And one thing I forgot to mention, Mr. Shigeoka, also one of the modest person I ever met, he mentioned he hasn't hold a doctorate, but I have to say that I was always impressed about his lots of deep knowledge related to water. Now we have time only for one question. Is there any question from audience? Anyone? Question? Then I have one quick question. If you could please tell us, is there any particular direction with this wonderful complex you would like to take, continuing as research? With this newly established laboratory?
Where is he going? Okay.
Yes. What is the next goal to take in the research? Does he have any particular direction to take, or continue working as we have been doing?
Okay, so I will answer in English. By meeting you and all the professors, I have learned how important and great aquaphotomics is. And by being able to see that, I was really able to find a place where I could apply this science to products. Even if we see it, if we don't apply it to products and make people use it, then it has no meaning. So using this technology to make people's lives better. So it tells us about us human beings. It's not just water. It tells us about our lives, the importance of getting to know your water better, knowing who you can be with the water and who you can connect with the water. So together with the products, I would like to educate the people and make sure that everybody can understand the importance of water, even if they're not scientists.
Thank you very much. And it's really wonderful because bringing science results to market usually takes more than 10 years. And what we can see here is really high above average. So thank you for this wonderful opportunity and great support. Okay, moving to the next presenter. Now I would like to introduce our next speaker, Dr. Jelena Muncan, who is not only an excellent research fellow, but a really very good and supportive friend. In her video this morning, she mentioned she learned a lot from me. I don't know what she meant, but I think I learned a lot more from her, and I have been really enjoying the collaboration with her in the field of aquaphotomics. Dr. Muncan, who is the right hand of Professor Chenkova, if I can say, has been working in Kobe University since 2017, when she started her postdoctoral research term in the frame of the Japanese Society for Promotion of Science Scholarship in Biomeasurement Technology Laboratory under Professor Chenkova's supervision. After her postdoctoral period, which ended in 2019, she decided that aquaphotomics will be her main field of work and stayed in Japan and has been doing a very fruitful activity in the field of aquaphotomics, marked by many high-level scientific journal publications. Her research is directed at reaching better understanding of structure of water in aquas and biological systems and their resulting properties and functionality. Today, she is going to present about aquaphotomic science looking at nature through water spectral patterns. Dear Jelena, please, the floor is yours.
Dear Zoltan, thank you very much. You're so kind, and it is lovely to see you. So, it is actually really an honor for me to have a last lecture. I began today, and I'm going to finish today. And I must say that that is something I could not have imagined. And I'm standing here finishing the first day of the Aquaphotomics conference, and before me there were such an amazing people, scientists that I admire for so long. They're like, I don't know, for maybe, how can I say, common people like movie stars. So it is such an honor, and I'm so grateful to Professor Chenkova and to all these professors and colleagues, people who worked with me, who actually brought me to this place. And I must say it was really such fun and such delight. So it is a big road that I passed, and I want to insist that it is a long road, especially because of the people who attended the workshop this morning. I really want to emphasize that anyone can learn aquaphotomics. You maybe see me now like, I don't know, a fancy person speaking languages and so on, but I come from faraway country, from a village where the rush hour means that the cows are returning from the pasture at 6 p.m. So it is really, everyone can learn it. And if I could do it, really, really, any person. So you just have to love that, I guess. So I'm going to start with some of the news that we have about the events that passed in between the third symposium and the fourth international conference. So what we did in the meantime, first at the previous symposium, we briefly mentioned that we're going to do a book, and internally we call this book Milk Book, but it is a summary of Professor Tsenkova's work since actually her starting of the, I guess, career in near infrared, and everything is really based, entire aquaphotomics is based on milk, on this first initial spectra that she took. So in this book, we put all of these results together. We actually updated many things because things change, we progress. So there are new interpretations, new meanings. And this book is going to be coming very, very soon. We are actually giving this to publisher Springer this, by the end of this month. So in this year, you will have very, very nice book about not only milk, cows, but also about the disease, detection, and of course how it is connected to aquaphotomics. Except this book, we worked on several papers, and I must say that we actually, so we published a small number of papers compared to the number of the papers that we are working on. So at the moment, I think we have at least around 15 papers that we are working with various scientists from around the globe. But I must say that I'm very grateful and I'm very happy to see that other people are working and publish more and more results, because they are. I'm always happy when I can learn something new. 2 years ago, I've presented like a graph which modeled the number of publications which mentioned the word aquaphotomics, and the number of such mentions was following the exponential function. So based on that model, we predicted that this year, so when I'm reporting about the number of mentions of aquaphotomics, we will have actually 133 mentions, and we are actually lacking 4. We have 139. However, that is probably due to me being late with at least 2 papers. So we published by the end of December, literally 2 papers. And when I've checked the last time, the number of mentions actually highly exceeded, and the number of our citations literally skyrocketed in January, in the first 3 months. So I don't know whether this is going to, this number, the progression of aquaphotomics is going to be exponential or even, explosive. But that is all thanks to you, all scientists across the world, from all these different laboratories. And I must say that I really admire people like Professor Vance and her student Mariana Santos Rivera, or Professor Shao, who independently started to do aquaphotomics on their own, because that's quite a venture. So another new thing that we have is that we asked for abstract, but we actually took from you extended abstract, and that enabled us to, for the first time, prepare actually proceedings, because these are extended abstracts. And the papers that we received, and we received several of the papers, we want to use to start a journal. This is something that we were discussing for a long time, also with the same publisher, Springer. So in the following 2 years, this is something that we are going to do to establish a journal. And I now would like to call all of you who attended the conference, who presented the talks or posters, to please just go back to the page, this page, at our website, conference website, find a template, and write a paper. We already have very, very interesting papers, so especially if your work is related to water activity, preservation, sugars, that would be amazing. We can then make immediately a special issue from the first number. Also, in the next 2 years, hopefully, I really hope before the next the 5th Aquaphotomics International Conference, that we're going to publish the Aquaphotomics book. So that would be that book is basically a summary of all our work until now, and it is going to be it is going to comprise really all contributions starting from the basic sciences, microbiology, agriculture, disease diagnostics, all this. So in the past, especially in the past 2 years, we really based our attention to the fields that are here labeled by stars. So in the last 2 years, we worked so intensely on this in these fields that I think it's going to be really a big book. In addition, what I've noticed from other papers that I recently get to review or find to read, I think that the aquaphotomics is going to include 2 more fields in the near future, and that is aerosol science or atmospheric science in general, and separation techniques in, for example, extraction and the purification of minerals, ores, and so on. So just a few, for example, really nice papers that you can read, which are showing like I would call them, model papers for aquaphotomics. It is aquaphotomics. The authors probably just didn't hear before. Regarding the aerosols, we're going to have one of the speakers who is currently involved with aerosols. That is a person from Austria, Professor Pierre Madel. So please stay in touch. He's going to stay for his lecture. He's going to present very, very interesting talks. The other thing that I mentioned, for example, separation techniques like waste, diversification, filtering, removal, everything that involves separation can have benefits from aquaphotomics. So in the book, we really plan to put all this, and as you will see from my talk, the leitmotif of my talk today is going to be everything is connected. So book is going to be a synthesis of that, and my talk is going to be maybe a preview of that synthesis. So what we know so far? We know so far to do analysis. We picked up all these absorbance bands. We understand a lot of things, but we still miss a lot. We still have lots of things to do regarding understanding of functionality, what each of these bands that we found mean. From my point of view, I sort of don't even care about the structure as much as the exact structure, because I'm not a chemist, so I don't understand those structures very well, and I see that the chemists are arguing between, oh, that is, for example, oh, you're sold with your models of balls and sticks, so everything is actually a wave, we have quantum energy and so on. So I really, until they settle on solution, I really do not care that much, because everything, so what each of these frequencies represent is energy. So I know that something is of higher energy, lower energy, so more capacity to do something, right, or less. That energy means something can be done, and I want to know what can be done, or what is the state of something, and that means functionality, right? So this is what I really like to know. That means basically understanding. So aquaphotomics is created as a science to provide explanation of everything, complete understanding of, especially what the life is, and it came as a response to all these isolated sciences separated, like genomics, which studied single components. On the other hand, aquaphotomics saw the water as this matrix, a scaffold that is connecting all these components, which has very, very sensitive hydrogen bonds. So the sensitivity of hydrogen bonds allow actually this communication, the constant interaction with the environment. So when we are looking at the water, we are looking not only at the components, we're looking at their interrelationship, we can see their dynamics, how they move together, what they do together. So functionality is something that comes as a synergetic effect. That is the property of the system. It doesn't exist if you only look at the components. If you just, dissect the human body, you know that the man is not going to be alive anymore. So that is something that is the same when we start to separate components. So that really reminds me, that is how I started my abstract, a little bit unconventionally, with a story, very, very long, from long time ago, Indian folktale about the blind man which wanted to examine an elephant. So this is that is the typical way of deductive science from before. Everyone wants to see. Everyone is looking at really just a little piece with some, let's say, specially adapted measurement technique for their field. So in the end, we really don't have a true picture of what our samples are, what the life is. This means not only, so this includes not only the sciences like biology, physics, or these omics disciplines that I mentioned. This is also the truth for spectroscopy. We are not still united. We are not using the entire spectrum as to the best of its possibility. So I want to emphasize aquaphotomics is not only enveloping and uniting all the like life sciences. It also aims to envelop and to bring together all these measurement techniques, so entire electromagnetic spectrum. And this is something that Professor Ozaki really, really nicely presented today. We really need the entire range. Every frequency is telling us something, and together we can make out the shape of this elephant of what life is. So we usually, for example, I usually interpreted, when I thought about aquaphotomics, I would usually see this like near-infrared spectrum with these huge two bands. But I really, so for example, I understood nothing about these, for example, second, third overtone, or this combination band. However, I'm really pleased to see, and I really want to thank to all of you here, because this program, the program of this conference, shows how beautifully we can contribute to each part of the spectra. So we have from ultraviolet region, from terahertz region. So each of us are bringing a piece of its own field, like, for example, Professor Vance and Mariana to diagnostics of disease in animals. For example, Sai Tanaka from Keio University to the understanding of workings of sugar and preservation. Well, not only preservation, but also how some animals or plants can survive very extreme conditions, like being in a very, very cold environment or totally without water. So we have really, really nice contributions, and I'm very happy that this conference turned out to be like that. What I want to also say, so I would like definitely to have more and more contributions, for example, terahertz and infrared. And when it comes to infrared, I recently, that is why I'm showing this to you, I discovered some very, very beneficial parts of the spectra. So in near infrared, this is the part that I really, really become to be interested in. And in infrared, this part, this combination band. So I've put here just one of the papers, which is very, very illustrative of the potential of something that we usually overlook. We just look at this huge band and we don't even bother to see this. Well, truth to be told, very, very often this we cannot even see this because there is very near carbon. We can see influence of the carbon dioxide from the atmosphere. But if we can have that region, it is very, very interesting. So this is the paper, which I think is quite good Aquaphotomics contribution for this part of the spectrum. So, as I said, the leitmotif of my ending presentation for the day is that everything is connected, not only size. I mean, when you look at the life, we are all part of the universe. We are all part of something bigger. We are definitely all connected by something, right? So, what I want to know about these connections is what they mean. So, what do they tell me about the things that I'm looking at? So. When I first read this paper from Professor Tsenkova, I thought in my abstract this is something like a Bible of aquaphotomics. When I read it now, I see and I'm like, God, she said that all that time. I read it. Of course, I read it 1,000 times, but lately I have aha moments. I really finally understand the meaning. What did she meant? Yes, of course, Womacs are the letters like ABC. That's the language of energy, language of universe, right? And the combination of these letters is telling you something. This is what tells you the story about what your sample is, how it's going to look like, what is going to happen to it. So, in brief, I'm going to try to present some of the things that we found out about this functionality, about the meanings of these water spectral patterns. So I will begin with one of the papers that we published. It was about quantification of fatty acids in liquid milk. That is quite a problem because in near-infrared people don't like liquid things, right? But so I didn't end up with very, let's say, surprising results. I managed to quantify the fatty acids in the region which is usually connected or traditionally connected with fatty acids, because it is connected to the absorbance actually of CH bonds, which is typical lipid. But what I saw is that to the accuracy of the model, I also had contribution of this part of the spectrum. And when I looked at the assignments of what these water bands are, it turned out that these bands here correspond to the absorbance of the same water species, and they were all proton hydrates. That means hydrated protons, so they can be hydrated by 1, 2, 3, up to 8 water molecules in this case. I had just small proton hydrates. So I was very curious, what does it mean, I mean, this proton hydrate? What does it work? And then when I searched, I found that this, especially this band, and I had this band as an activated band for absolutely each fatty acid. It turns out that this is the band which would appear in the spectra of any proton hydrate, that doesn't matter the size. So you will always have this. This band that in connection to the functionality of these fatty acids in milk, I will have proton hydrates. And then I found out that I had to search what the protons actually do and what would that mean for my samples. And it means that actually protons are essential, and proton transfer is essential, a major force for self-organization. What does it mean? So it means that, for example, whether fatty acids are going to be separated, like each for one, each isolated, let's say, or they're going to form something called micelles, like a global form, or maybe they're going to be, like create aggregate and something like that. So this told me the first thing that, wow, this is something, if I have protons and proton hydrates, that can mean something about self-organization. Then I had another study, which was totally unrelated to fatty acids. It was actually about environmental analysis, environmental protection. We wanted to quantify, actually not me, Professor Inui and my colleague from Serbia, Vlada. They wanted to quantify some very persistent substances in the environment. They're coming from, for example, Teflons, the products that we use in the kitchen and which allowed to cook our food and not to get this food stuck to your... I don't cook very much, so obviously I don't have the vocabulary. So these substances are very persistent in the environment, and they wanted to know if aquaphotomics can help measure them. So we prepared lots of dilutions of two types of these contaminants, which were quite similar. They had this one tail and hydrophobic tail, and they had just a little bit different head, which is polar, which means likes water. So we had them in in various concentrations, and contrary to my fate, actually, in aquaphotomics, I could not develop nice models for quantification. And then, so actually, I ended up modeling one of them only with raw spectra, which told me, oh, I have scatter. So in this case, if I have scatter, inside of these solutions, I have something which scatters light, which means it's a structure, something. Then I did some, let's say, chemometrics, some gymnastics with data, and then I ended up with a water spectral pattern like this. So these are water spectral patterns that describes average of these solutions. So the green line corresponds to one of them, the blue one to the other. I managed to quantify the one called PFOS. So PFOS showed the difference compared to the other compound in this absorption of protein hydrates. And then I realized, oh, I have scattering structures, I have protein hydrates here, I have structures, I can measure them because I have something created, and that is called micelles. So then are little spheres of these molecules. So when I Googled micelles and absorption of water, I realized there is something, especially in papers published by Japanese scientists, let's say from 20 years ago, they found out they actually have had this water absorbance band around 1420. We call it hydration water. This is the water which is involved in those Japanese papers with hydration of micelles. And in my case, I think it is related to hydration of micelles. And I later, based on some other works, realized that this is the water which hydrates amphiphilic molecules, molecules which have parts that love water and parts that don't like the water. There is a poster about this work, so please go to the website, look for more details. The interesting thing, what I wanted to say about the micelles and about the self-organization is that I usually connected previously, before I learned about the micelles, I knew that this water hydrates proteins. I've learned that from Professor Tenkova's paper about the prion protein a long time ago, and from a more recent paper about amyloid. So that was the first thing that I knew about this water band around 1426, that it hydrates proteins. I didn't know it could hydrate something else. So, for example, I found this band when I examined soft contact lenses, which were worn by people, and those which were new. Those which were worn, which were placed in the eyes, had, for example, this band, and when you actually place contact lens in your eye, structures from this water that hydrates the eye get attached. So I detected that I had protein deposits on the structure of contact lenses because I detected this water. This is what I knew then. So coming back to these guys in water, these pollutants, the point is that what we realized here that this water may not be very good when you detect it, that it may be related to actually misfolded proteins, and that can help detect other things such as disease. One more thing that when I looked at this spectral pattern, I also noticed that there is a very interesting ratio of waters, of something we usually call free water or less hydrogen bonded water, and hydrogen bonded water. Now, the ratio, when you have a lot of this free or less hydrogen bonded water to hydrogen bonded water, it means that you have very good wettability. So this solution, for example, is going to spread nicely over the surface like this. And this is exactly why these compounds are. They're surfactants. They actually are supposed to spread over the surface and to allow the spreading over the surface and not, how to say, gluing. So in this regard, about wettability and surface tension, Professor Masato Takeuchi and Professor Aoife Goen have very nice talks, especially Aoife Goen, she connects all these things with biocompatibility. That's very useful. To go back to the fatty acids, when I said that I had in 2 places in the spectra the same bands, the other part of the spectra was around in between 600 and 1800, sorry. So that also started to appear in my results more and more often. And for example, one of the latest contribution is from K University, from Tanaka-sensei, who also has a lecture about this. The point is that in this region, we start to recognize more and more water absorbance bands. And she actually detected in a very, very nice experiment, fantastic experimental design in my opinion, that there is one band which is really related to hydration of glucose and allows distinguishment between the different structures of glucose. And I think that all this is because of the charge, because of these protein hydrates. Because if you have hydrated charge, it is sensitive to charge. So in this regard, also please follow the 3 speakers' names that I put here on this slide, because they also, especially Justyna Grabska, she really made a fantastic. She will have a fantastic talk regarding the sugars. And you can also see a poster, which also my colleague Vlada, who did those contaminants analysis, who also did the results with sugars. So take care to take a look at that poster. One of the other things that we did in the meantime is yogurt. We experimented something with yogurt. And with yogurt, for example, we found, again, this, for example, protein hydrates. We found something we call solation shells. We also found, I call them sugars, but that's carbohydrates. And in this case, for example, for yogurt, this part means thickness. It means you have large carbohydrates which are able to be hydrated, and this creates texture in the yogurt. So based on the water, you can know whether whether the gel in yogurt is set up. So this is something that these parts of the spectra can tell you. There is one more fantastic study that we had the honor and the pleasure and I don't know how to thank to these people, to Professor Paolo Oliveri, Cristina Malegori, and the Italian group who presented 2 years ago part of this study about the preservation of rice germ during 6 months of storage. That the analysis that we've continued to work with them opened up so many topics and brought so much understanding. For example, during the preservation of food of this rice germ during storage, we saw a pattern of 3 bands. It is very interesting because I saw these bands, 3 bands on other place. I saw them on the spectral pattern of a water vapor. So I was thinking like, we have preservation of this rice germ. We know that for preservation there is something which is crucial. It is water activity, and water activity is connected. It is connected absolutely to something called partial pressure of water vapor. So I was like, wow, I can't believe I'm seeing water vapor, right? So this is something that was, it's interesting. We found vapor in food, right? Then I connected the same 3 bands in from another paper, which was exploring apples, texture of apples. And in this case, the pattern, the presence of vapor, was showing mealiness. That means when you bite an apple, you don't have that juicy feeling. It feels, like dry. So that tells you something, this pattern, when you have it, tells you about the structure. In addition, we learned about these absorbance bands, and these absorbance bands are so fantastic. In brief, because I know that I don't have any more time. So these 2 bands, when you see them together, they indicate damage. This is the strongly bound water. If it is lost, if it is decreasing, that means your sample is going to be damaged. In the same time, you're going to have changes at this band, which means dehydration from the cell. So not good. When you have these waters, not good. These 2 bands indicate the water activity, and they present basically a balance between hydration, water, and something, and this water around, which absorbs around 1455, and which is the water that is adsorbed, that is on the surface, and that is easiest to evaporate. This is the water which is lost immediately when you heat up the sample. Or, for example, this is the type of water that when you start to dehydrate plants or dry plants, this is the water that will first go out. And this is the water that will in the most easy way communicate with the environment. And this is, I think, currently my favorite band, 1436. So 1436 is here. It means phase transition. It means preservation. And I'm so happy I found it. And I think we will have this band repeating more and more, and in connection with what the life is. So as I said, this study created an avalanche of questions and of the things that we understood. And this is what we're doing now. We're trying to understand what the life is, for example, or when we study bacteria, we want to know why this water activity below 0.6, what does it mean? What this number means? What is going on with this water? There's also several other questions that are very much related to these bands. And one of them is why we have so different food preservation methods. We have so many different, we can put salt in the food, we can put sugar in the food, we can dry the food, we can freeze the food, we can put some acid. So how come we have so many different types of preservation directed at and performing one function? So it is because all these substances are influencing the water, right? The other thing, for example, what I realized, and it is connected to this phase transition and the interaction between sugars and water, and also, I think, between anesthetics and water. One of the questions that really puzzled me for the long time, why anesthetic? So when I put anesthetics, I know that I don't feel pain, but when I put the cold pressure, for example, compression, I also deaden the pain. So how come, what is going on? Why is that? And I think it is because the nature works very, very simply. It just changes, it balances different waters. This is something that I said, you will have this presentation, you will have this talk, so please go ahead, use these bands as an indication of damage. This is something first saw by Professor Gowen, I think. I really need to say, I don't see her here, but a big, huge thank you to Bream, our student, who is an amazing, I think she's the best student that I ever had, who helped me do this amazing, amazing work with water activity. And I think you will hear her name in the years to come. She's just, imagine. she has a poster. Go to her poster. She did amazing work with lots of different food systems. And what I really, really like that this work for me resolved, I now know that the moisture and water content are not the same. And I know that the what we call combination band and first overtone band are not showing the same information. So that is something that I hope we will publish this year. So in general, from my talk here, the conclusion is about water. My conclusion is that we have a simple rule which can be called likes, likes, likes. So in this region, we have, for example, hydrated protons, that means charged molecules hydrated. This is, these are polar molecules which are similar to polar water molecules, right? Here we have a type of water which hydrates substances which are neither, like those surfactants that I mentioned, like proteins that have both polar, I mean water-loving and water-fearing part. Then we have this undecided water that can easily go there or here or so on. And we have strongly the water which creates hydrogen bonds with itself, right? That's water which hydrates water. So what I presented here is like endless. You read one paper, you do one study, you end up with so an avalanche, and everything is connected. I'm very, very grateful. I know that I overstepped my time. That so any questions, please put in the chat. Send a video of your question, and I'm very, very grateful for your attention. To all of you who worked with me for the past 2 days, I could not have I could not have a chance in half an hour to mention each of you, and I am grateful to each of you, and of course to all our wonderful sponsors, and to company Dr. Risela, who is going to help us do this fantastic research in the next 3 years. And of course, where is she? She left. I killed her. Sorry. So I'm very, very grateful to all of your attention. It is late, and I think we can finish for today. Thank you very much.
Thank you very much, Jelena. I hope people will apologize me. I can't stop you because it was really very interesting, and thank you very much for this very nice presentation. I'm amazed. I was always amazed by your energy, and I'm amazed again. I can see you have lots of new plans. And you again opened our eyes, and now I understood what Professor Chenkova often said, that sometimes we have to narrow down, sometimes we have to go more wide, and yes, now I understood this again. Thank you. Anyone has question to Jelena? We have probably time for one quick question.
Okay.
No question?
Well, they can write. I'll be happy to answer.
All right. Yes. So I would have many, but I will not start now. I think we will have another time to talk.
Yeah.
Thank you once again very much.
Thank you, Zoltan.
And then with this, I would like to close this session. Thank you very much for all the presentations. I think this was a perfect title, Further Developments, because we saw very nice presentation summarizing technical overview of near-infrared spectroscopy, wide range of instruments and chemometrics, and also practical applications. And I think it was very nicely closed with possible future directions. So thank you very much. Thank you very much for your participation. And I wish you very good evening or afternoon, rest of the day. And let's continue tomorrow.
Let's continue tomorrow.
Bye.
Thank you, Zoltan. Thank you all. Tomorrow.